Hey, John here. Let's talk about how we analyze the efficiency of an algorithm and express the results of our analysis using what we call big O notation. All right, let's look and see what we mean by analyze and complexity, right? Well, we're referring to time and space, all right? Time, it simply means how long does it take a program to do its job. All right, and quite often you can express that by predicting how long it's going to take based on how many input elements you give it. You know, if you process a bunch of data, how long should you expect it to take to give you an answer? Like if you're sorting a bunch of integer values. It's a trivial example. Let's sort something, right? You know, well, the amount of time it takes to sort should be related in some way to the number of elements you're sorting, right? So how do you express that? You know, if you use method A, it might take a different amount of time than if you choose some other method B, right? Okay, so that's one kind of complexity. There's another kind that has to do with how much memory does it take to run your program. All right, so now we're dealing with time complexity and space complexity. All right, and when you choose algorithms, sometimes you can waste a ton of memory, but it'll go real fast. But maybe you can't afford a lot of memory, and you have to use another algorithm. Well, you can save a lot of memory, but maybe it'll take longer to run. Okay, so quite often you want to know both of these because you'll jockey these amongst each other to kind of optimize the problem, to save money or save time, right? Okay, more often than not, time turns out to be a big concern, right? Because you can always storage is one thing you can usually throw money at that problem. If you have money, you can always buy more storage. But if you miss a deadline, you know you failed, right? So quite often you talk about time, but this does come up in both of these domains, both time and space. That's the takeaway there. All right, let's focus on time for the discussion here. The same thing ultimately applies to memory. It applies to anything. Any resource can be expressed using these techniques, right? Quite often, however, in computing and where algorithms are concerned, analysis of their performance, you are pretty much focusing on either time or memory, all right? And you end up with functions. These are very realistic characteristics, as we'll see, for various types of algorithms. All right. So what does it mean in terms of time? Well, if it takes 1 nanosecond is what this means. If you have a 1 gigahertz processor, right? And I know a lot of you are, oh, I got a 5 gigahertz, but these are operations per second, not clock ticks. Turns out many clock ticks were probably required for the average instruction on whatever kind of CPU you have today. And clock speeds up to on the order of 5 gigahertz are not that uncommon, but 1 billion operations per second are probably still pretty reasonably optimistic on most systems today. All right, so these are somewhat realistic numbers. So, well, how long does it take to process n items at 1 billion per second, right? Well, that's 0.01 microseconds, or 10 billionths of a second, right? Well, how about 20? Well, that's 20 billionths. How about 30? And so on. So this thing, when you have a system that consumes 1 unit of time for every element of input, you say there's a linear relationship here. The time takes n units, where n is the number of elements. Okay, there's other things you can do depending on how you write your code. This is a very common situation that you run into as well. You might end up with an algorithm that uses log 2 of n time to run. Well, that would be better, right? If you choose an algorithm that takes this long to complete and you burn up this much time, you have this other one available to you, you'd probably be better off using this one, right? Especially as n increases. And you're going to see this is the whole key here. As n increases, what happens to the amount of time that the algorithm uses? Well, down here, n log n takes a little bit of time, right? But eventually you end up with the situation where n becomes, look at how big it gets. We're at 0.1 seconds. Well, he's still down here at 0.23 seconds. So this is, or microseconds, I say, right? So this is seconds and this is microseconds. So this is much faster, right, than this one over here. Okay, so this is actually a better bet if you have to choose between two of these things. Well, what if you end up with n times log 2 of n? Well, that would be bigger than this one, right? And it turns out a little bit bigger than just n, right? And that makes sense. It's these two multiplied, and it takes this long to do these. If you have an algorithm, if you must use an algorithm and there's nothing better available to you, you can estimate that it would take this long to process that data. Well, what if you end up with an algorithm that takes n squared units of time? Well, now you have a problem, right? Look at this. If you're running an order, well, you'll see this is order n time. It's hard for me to actually not work ahead in this dialogue after using these words for decades. If it takes n units of time to do, what is this, 10 million units of work, right? If it takes that long in an algorithm that uses n units of time, well, an algorithm that uses n squared units is going to take a lot longer, right? This is more than a day. Well, what if you end up with an algorithm that requires 2 to the n power? And again, these algorithms all exist. This is an enormous amount of time. You're not going to be around long enough to handle even 100 data elements. If you are forced to use an algorithm that requires 2 to the n computations where n is more than 50, okay? As you get up there, you're already, this is outrageous. Okay, so just to give you a little hint of where we're going and the kind of magnitudes of numbers here, all right? So let's graph what you were just looking at. As n goes up to 8, right? This line here is the bottom one here. It's kind of light. It's hard to read. Let me zoom in on that. Maybe we can get a better look at that. That's your 2 to the n. That's your giant one that we'll all die of old age before it's done kind of thing. And what are these other lines down here? Well, this is going to be your n squared. This is going to be your n log n, and your log n, and your n. It almost looks like n is free, right? Because it looks like a horizontal line here, compared to these other ones. So as we zoom in, even the n squared starts taking off relative to these other guys. But our number of items is going up, right? Now we're looking at 20 items. Up here we were looking at 8 items, okay? So this graph is showing us what happens as n increases. And we're throwing away, as we go, the ones that shoot up just so fast that they're just a vertical line, okay? What is this guy showing? Well, now n is going up to 100. And we've removed the n squared because n squared shoots up just like 2 to the nth power does. You might as well, we could have left it on here, I guess. It would just be on the y-axis here. We just shoot straight up. N log n looks like it's growing pretty quickly now as well. Again, as the number of items goes up, you become increasingly sensitive to the type of algorithm that you've chose. So Tn over here still looks like a straight line. It looks like, you're getting everything for free. Okay? And even n log n looks outrageous as the number of elements starts to increase significantly. Now, and again, think about this, right? This is only 1,000 elements. 1,000 is not a big number if you think about it. What if this is like the number of employees somewhere? Or the number of web pages on the entire internet that includes some word in them, right? Well, you certainly don't want to use a 2 to the nth power algorithm to search for web pages, right? Google, I'm sure, is not using algorithms like that to deliver your search results. It would just take forever. They couldn't ever complete, all right? So what happens? We keep growing, we keep zooming in, and now we're what, at 10,000? And what do we got here? This is log n up here. Or I'm sorry, this is n log n right here. And log n looks like it's flat. It even looks like it's as free as just order n time. Uh, and you grow and grow and grow. And what are we at? Up to 1 million now. And these things are still diverging here, right? But log n still looks very flat. Log n kind of is if you zoom way in on log n, it's a curve that goes up and then sort of levels out as it goes. So it looks very flat. It's not a bad choice. In other words, it's a wonderful choice to make compared to all these other ones if your number of elements is on the order of millions, right? Here's our million, and these are still looking about the same. So again, and look at this time, right? This time number is getting pretty darn big. All right, so what is the size referring to in all these examples? Like I said, most of the time I think of it as like the number of elements that you might be searching, or the number of elements that you might be sorting, or something like that. But there's other things you could do with it, right? If you have these two arrays of data and you're going to merge them into one, it might very well be that n refers to the total size of the resulting merged array. It could also be something like, you're writing a program that calculates and prints out a bunch of Fibonacci numbers. Well, n might be how many Fibonacci numbers do you want to output? Or it might be the factorial that you're creating. Okay? So the whole thing is that it refers to some quantity that's fundamental to the algorithm. And like all things in life, there's not necessarily just one of those. There can be problems where, like, let's say you're merging these two arrays. You might have two n's. The complexity of the algorithm might be based on the sizes of the two arrays, not necessarily dependent on the size of the resulting merged array. So sometimes you might end up with a situation where you have two different n values, all right? It could be that if you have a small array merged with a big one, it could end up with a different amount of compute time than a big one's merged with a small one. You'd want to order them appropriately if the relative size of the two mattered in some way. Now, before we get to the conclusion of this dialogue, let's talk about exact values, right? Now, it might be possible to actually be able to calculate and know for certain exactly how long some algorithm takes, right? You might know how many exact bytes of data that were read in. You might know exactly how many machine instructions are going to be executed. And you might know that the data itself will not impact the number of instructions executed. For example, sometimes when you sort things, the contents of the data elements can change the amount of computation time that is needed, right? I mean, if you think about it, if you have a data array that's already sorted, one algorithm that sorts things might take advantage of the fact that if it's already sorted, it will optimize itself and terminate more quickly than other algorithms that are just going to brute force sort it anyway, even though it's already in order. Okay? And we'll see that as we go along here. What's the takeaway here? Sometimes you can't actually know how long it takes to run a program because it might be data dependent, even if you know exactly how the code is implemented. Now, I can take that further. If you have a higher level language that goes through a compiler, or even worse yet, an interpreter, things like this might make a difference. If you code x is less than 10 in a condition, like if x is less than 10, do something, or you otherwise code x is less than or equal to 9, these might actually take it might take a different amount of time to run. Now, granted, usually a compiler is going to optimize this. Even if you wrote this, if the machine can do this more quickly, most compilers will choose the faster of the two, but not necessarily always, okay? So, what's the takeaway here? We don't know for sure that the compiler will do the best possible thing in all cases. One machine may behave differently than another one. Or even a different, release of a CPU by the same vendor. And next year, the upgraded PC might actually execute this code completely differently than it did last year. Now, this is a trivial example, right? There are much more complex examples. You can extrapolate this way out, and you can come up with all sorts of things that you just cannot generally know for sure. All right, unless you analyze the output of your compiler or the exact version of an interpreter and look at the exact number of instructions running and know for a fact that you know exactly how many instructions are going to work, you're going to end up in a situation where you're going to have to simplify your estimates. You're going to have to estimate, okay? And like we say here, we're going to make seriously major simplifications. And that's a good ticket for you guys, right? Because you can simplify all these mathematical equations we're about to look at all the way down to just some really simple things. And this is all going to make our lives a lot easier. All right, so what does this all mean? Like the sorting example, you know, you can have the average time, the best possible time, or the worst possible time. Sometimes you can kind of guesstimate what the worst case would be for how long it takes to search a database or how long it takes to sort it, okay? You might even be able to estimate the average time or even know the best possible time. It turns out, no matter what you want to deal with, the worst case is quite often a really useful thing to know. Like, you know, how long does it take to process the image data from some cameras in a self-driving car? Well, you know, somebody might say, well, the best case scenario is that it'll get done and you won't die. Well, what's the worst case scenario? Well, 50% of the time, it never gets done in time to stop, stop the car to avoid hitting a rock in the road or something like that. You may really want to focus on that worst case in those scenarios, right? Well, it turns out in a lot of situations, the worst case is your number one focus, right? It's great to know what the best case is, but you need to know what the worst case could be, because it will come up from time to time. Given enough data, you need to know if the thing is going to finish in a reasonable amount of time. All right, so let's go from the easiest to the most complicated kind of problems, right? What do we mean by constant time? Well, we say that an algorithm runs in constant time if there are no loops and it doesn't include, calling a method whose time is unknown or is not a constant, right? Well, these all make sense. In other words, no matter what you ask it to do, it's going to finish in the same amount of time. No matter how much data you give it, it'll finish in the same amount of time, okay? That's constant time. So if a statement involves a choice, like an if or a switch statement and stuff like that, each of which takes constant time, it's still just constant time, all right? Let's look at this algorithm here and analyze how much time it takes to run. So, what is the bottom line here? The bottom line is my font is not quite perfect, but I think we can make it out here. What are we doing? We're reading two numbers from standard in into num1 and num2. Then we're asking if num1 is greater than or equal to num2, do something, otherwise do something else, and then print out this value. If you add up all this stuff, and what you find out is that either line 4 or line 6, right? If you have if, then it's going to do this one. Otherwise, it's going to do this one down here, right? So it turns out that no matter what you do, you've got one, thing to do here. So we got operations. We got one operation here. We read in two items, so we're going to call that two operations. We ask a question. That's one operation. We're going to, if the question's true, we're going to do one operation inside here. Otherwise, we're going to do one operation down here, and then we're going to do some stuff down here. We're going to print out three items. The maximum number is this, that, and then print end of line. So there's three operations down there. You can add all this stuff up by observing that either line 4 here or line 6 here will execute, but not both. Therefore, no matter what you do in here, it will always take this 1 plus 2 plus 1 plus one of these guys plus 3. Okay, so there you go. You got 8. No matter what, this runs in constant time. And it takes 8 units in this example. Linear time. Well, linear time is, there's no squares involved in this thing, right? There's no exponents, right? So what is linear time? Well, if I say I have a loop that goes from 0 to what here? 0 to n, okay? and then I add 1 to I. So this is going to run n times. It's going to execute this loop n times. And what's going to go on here is it's going to have some constant plus the number of time units of time to execute this inside here, plus another constant like the setup time. So what do we got going on here? K is how long it takes to go through the loop once. Okay, n is the number of times it goes through the loop. So you got, that's why you have n times then this constant here is the amount of time it takes to do this one line here, and then plus c, which is the amount of time it takes to initialize the loop. So you say it's k times n plus c. This is linear in the n, which is going to be the number of data elements, or the size of this array in that domain. All right? That's linear time. Here's another example of the same thing. You've simply got a loop here. It runs until num is equal to -1. So while it's not equal to -1, you're running through here. It's just summing up a bunch of things until num wanders into -1. It's gonna add up all the numbers between 0 and 10 in reverse order, right? So what do we got going on here? We got a bunch of things going on. So this is all up here will be done once. This will be done once. This question will be asked a number of times. It'll be asked basically num times, well, plus 1 really, as it wanders over to -1. This down here will be done roughly num plus 1 times, and so on, right? So let's see what happens when we add it all up. When you're done, of course, this will be done one time. So we say what? The loop body is 4 operations that happens n times, right? Some number of times. The check is 1 operation, and it's done 1 more, because the last time you do this, this question is asked, and the body is not executed. That's why it's n plus 1 times for that. And you got 4 operations that are done outside the loop. You're looking at 4n plus 1 plus 4 equals this many time. This is many of time units that this program will run. Okay. And what do we got? As we do the math on this, as n gets large, what's really happening here? We have n, and we have 5n plus 5 over here. Well, look what happens to these terms. As n gets sufficiently large, the 5n here dominates the value in this column. As n gets larger, this plus 5 becomes so insignificant, it means nothing. And again, we care about things as they get large. It doesn't really matter if your problem is tiny. It's going to get done in a reasonable amount of time anyway. But what happens when you get a lot of data? Well, we speak in terms of this 5n is the most important aspect in this example. We don't even care that the impact that this provides. Because what is that? In a percentage basis, that's 0.01% down here. And that's only with 10,000 elements. As you get into the millions and so on, it's going to be 0.00001 and things like that. It doesn't matter. Okay? So we throw that one out is what we're going to see. It becomes a negligible contribution. And this is a 5n is the dominant influence in the amount of time that it takes that thing to run. So constant time is a pretty good deal, right? If it only takes you, 5 units of time, no matter how much data you give it, that might be a pretty good choice, rather than, hey, it varies with the data and it starts taking a lot longer. So here's an example, right? So let's say you got 2 different options, and you've got algorithm A, and no matter what you do, how much data you give it, it takes 5,000 time units to finish its problem. And let's say you got algorithm B, and somebody goes, oh, I've done a lot of work on this thing, and this one takes 100 n time units. Well, when n is like 1 or 2 or 3, algorithm B is better, because it only takes 100, 200, or 300 time units in that scenario. But as n gets bigger, most specifically as n gets bigger than 50, now algorithm B takes longer than algorithm A, and as n continues to get larger and larger and larger, algorithm B takes longer and longer and longer to finish, while A takes the same time no matter what. A is the sure deal. It's the sure thing. B, you might win. It might be nice if the n is small, but it's a horrible choice if n is large. Okay? So what does this really then mean? We need to keep an eye on large problems. That's where we're really going with this. It's not necessarily always the scenario, but more often than not, we really want to look at problems as n approaches infinity. And in this case, algorithm A is the better choice when n is bigger than 50 as it approaches infinity. All right. Now, what about those constants? Like I said, these are not so important as we go along. So here's kind of a more mathematical view of the situation. What really happens here? When we have, some function, no matter what it is, whether it's just n or 5n or something, plus this constant, well, the constant becomes less and less important as n gets bigger and bigger and bigger, right? Assuming, of course, the degree of n is greater than 0. In that scenario, this c here becomes less and less important as n gets bigger. If you have a k times f of n, well, it doesn't get less important, but what happens is, if you abstract this out, right, if you don't know what this is, right, and you do know that this is some kind of a constant, right, well, you can do things like reduce that constant, and yeah, it'll have an impact. Like cutting a in half cuts the time in half. But that's not all that concerned, because if f of n is not a simple linear function, if f of n is neither constant nor linear, if it becomes polynomial, this constant over here is not very critical. You're more concerned, again, about what happens in this function here is the point, all right? And yes, you can reduce this if you want, and if it's easy, definitely you should. Don't be wasteful, all right? And usually what you're going to have to do is optimize your code. Sometimes you got to be quite careful about that. But ultimately, if f of n over here is polynomial, then this really doesn't matter at all. You can ignore it. You need to focus on this thing, all right? So bottom line, don't worry about these constants. Whether you're adding a constant or multiplying by k, this is not a huge deal. All right. So how do we take advantage of all that to simplify the formulas here? All right, so what are we going to do? If you got a 12n squared plus 35 formula in here, well, throw away the 35, throw away the 12. They won't really matter that much. N squared is the dominant force in this formula as n approaches infinity, but overwhelmingly so, right? Now, we can continue this on further. If you have a polynomial and you end up with, beyond, n to the 1 power, n to the 2, n to the 3rd, and so on, you just take the exponent, the highest exponent in here, the highest order term, and none of the rest of this will ultimately matter. Again, as n gets big, this is the dominant part of the equation. So if you end up with something, when you add it all up, you end up with an equation like this. We say n squared is the complexity for that function. Now we move on to how you're supposed to say these things, right? What we call this big O notation. If you end up with a situation like we just talked about, here's an algorithm. Oh, it ends up taking 12n cubed plus 4n squared plus 8n plus 35 time. You don't want to say this when you're talking to people, casually, in the lunch line like we all do, and talk about the complexity of our algorithms. Well, you're going to really refer to this as just n cubed, like we just said. Throw everything away, throw the constants away, throw away anything with but the largest exponent. This is an n cubed problem. We say, if this is expressing the time, it runs in order n cubed time. This is a big O. And the way you say it is just like I just said. This thing takes order n cubed time. And again, how do we justify this? Here's a table that shows the math that we just looked at. And I iterated 3 times. As x gets larger, what happens? Well, here's your x squared, here's your 3x, and here's your 5. It's the function we were just looking at. X squared plus 3x plus 5. As x gets bigger, what really happens? Well, 5 never changes. 3x grows, but x squared grows a ton. If you add all these together and use this entire function, well, you know, the 5 is the dominant thing here when x is 0. When x is 10, 135, well, you know, everybody's kind of contributing a little bit there. But as this thing gets bigger and bigger and bigger, we're already, even at, what are we looking at? Even at 1,000 elements, even at 100 elements, right? This over here, the 305 is your 3x and your 5. That's only, what, 3% of the entire time here. And that's only with 100 units of data. As you go to 1,000 units, what are we looking at? 0.3% of this whole number. 0.03, 0.003. This is absolutely insignificant. That's why we can just, like I say, just ignore all this junk and focus solely on the highest order, the highest degree term in any polynomial. So let's look at this thing. As we graph each of the elements you just saw on the graph we were looking at, these 2 lines here, this one here is your n squared, and the one up here is the sum of the 3 terms. It's this line plus this line plus this line. And yes, it's more, but let's look and see. And this is only with n equals 10. As we move to n of 20, look at how close together these get already. And we're only at 20. As we go to 100 or 1,000 or 10,000, these 2 lines converge and these 2 things flatten out. So we can just focus on this n squared line because that will take over and dominate this graph as n gets bigger. Now, these are the common types of complexities that you're going to see in a lot of algorithms. They fall into these, a lot of algorithms, you'd be surprised, fall into just these categories. All right? Now, these are sort of, the one on the top is generally the best. If it runs in order 1 time, it takes 1 unit of work to do whatever, process whatever amount of data you give it. Now, that's a good deal because the log of n is always less than n, right? Then you have just order n, and then n times log n, which is obviously going to be bigger than n and bigger than log n. So that'll come in here as we look at how things slow down as they become more complicated, right? N squared, then n cubed, n to the kth power, right? And then you have 2 to the nth power. All right, these are, you know, up here we're still dealing with, you know, polynomials. And once you get down here, this thing is going to, you know, as n gets big, the time goes up almost immediately, okay? Again, as n approaches infinity, these guys down here just explode really fast. Now, related to this whole thing are what we call NP-complete problems. These are problems that run in non-polynomial time, okay? A lot of the stuff we've already discussed are what we call efficient problems. They run in polynomial time. Well, NP runs in non-polynomial, which means it's worse, right? And there are not only worse problems in terms of time, there are hard problems in that domain of problems. Some of them are even harder than other ones, is the point. And those are called NP-complete problems. They're interesting to mathematicians and computer scientists, right? It turns out they're a class of problems. I mean, you get to win a Nobel Prize if you could say, hey, I can find an efficient solution for one of these NP-complete problems in this domain of problems. It turns out that if you can solve one, you can solve them all. This would be an enormous contribution to science if somebody found a way to do this. And there may very well be solutions to this class of problems in quantum computing. Once that becomes realized and cost effective, we might be able to solve these NP-complete problems with that type of a completely different way of processing information. Now, I mention these because they do arise surprisingly often in the real world. You know, the real world is a complicated place. You know, all problems aren't easy, right? And you need to be able to recognize when this happens to you. because you might be finding yourself in a situation where you're trying to solve one of these NP-complete problems and not really know it. It's a good idea to be able to spot them when you get into this situation, because what you really have to do in those cases is kind of find a simple way of approximating the solution. You can't really run these things to completion because they may not end ever using the known solutions we have today. So there are various ways to kind of like cut short and say, well, this is find a solution to a problem. It may not be the best one, but you have a solution, and that you're going to have to just live with that, and accept the fact that you can't find a good enough one in a short amount of time. That's the whole point here. So here's a well-known problem. Let's say you got a traveling salesman that wants to visit a bunch of customers. He's got one customer in each city. Okay? So he's got a list of cities. And you want to know what's the shortest way to visit all my customers. Well, what do you need? You got a list of all the cities. You need to know how far apart they all are, right? Let's say he's driving a car or flying a plane or whatever. So the amount of distance between each of the cities is going to be proportional to the time it takes the guy to travel, is the point, right? So what is the shortest path he can take? It turns out this is not an easy problem to solve. As the number of cities goes up, this is the complexity of this thing just takes off stratospherically immediately. Now you can find solutions to the problem, but if there's enough cities in there, it takes forever, quite literally, to find the best possible solution. Let's look now at some code so we know how to recognize these things. I want to do a big O analysis of this code right here. So I got a loop. What does this loop do? It counts from 0 to while I is less than n. So this loop here will execute its body, which is these lines down here. Will execute the body of this loop will execute n times. Well, what does it body do? Well, this body does another n times. It does this. So this loop is going to say, I want to do n times, and this one's going to do n times this. All right, let's just say this is one operation, right? So how do we figure this thing out? Well, I got n iterations of that constant 1 unit of time in the innermost loop here. So simplify this, what do you end up with? K times n squared. So, as we said, throw away the constants, keep the highest polynomial, or keep the item with the highest degree. That's my answer. This is an order n squared problem right here, okay? We don't really care about the k at all. N squared is the dominating factor. Here's another one. Now I got a loop that goes from 0 to n. This one inside of it goes only from 0 to I. So this is actually less executions than the previous one. And then inside that loop we do one item of work, which is a constant in here. So what is this one going to do? Well, you should recognize this from high school algebra. This one's going to average out, right? You got n, and on average this is going to be n over 2 of these times the constant here. So it ends up looking like this. So where I varies from 1 to n, you calculate what? K times n minus 1 over 2. You see the n squared hiding in here when you calculate all this out. You got k of times n squared minus k minus 1, and all the constants factor out, and it leaves you with your n squared. So this is also an n squared problem. Believe it or not, they're the same as far as big O notation is concerned. Let's look at this one. We got a loop that is going to execute its body, what? 0 to n, that's n times. Here's one inside here. There's a loop that's going to go n times as well. All right, so if it ended right here, that's the same as our first example. That's an n squared problem right there, right? So in addition to that, it's going to do this loop down here, which is going to execute 2n times, all right? So you've got n times the body of the loop, which is n plus 2n. And each one of these loops does, order 1 type of thing, so we don't worry about the body. These run, this is constant time, that's constant time. And you know that that's going to factor out because of the rules. So how do we do this one, right? Well, that's your n here, is this n over there. This n here is this one right here. And this loop here is your 2n right there. So do the math, right? So we got what? N plus 2n is what? 3n, right? And you multiply that by n, so you end up with 3n squared, okay? Throw away the constant. That also is order n squared. Again, as n approaches infinity, this is going to take n squared time. All the other stuff in there really won't matter. Here's another one. What do we got now? We got a loop that's going to run n times, and the body is like this, so you have what? There's another n times of this. So again, this is the same as the previous one, but this one down here is 2n, just like the previous one, and there's a nested loop inside there, which is another 2n times this one that's constant time. So you do all the math here, right? This outer loop is n. You notice these parentheses here are kind of like where the curlies are here and where the curlies would be here, although they're optional, right? So you got, what? You got n times, and then this n here is this one right here, and you're going to add on this 2n here times the body of its loop, which is 2n times the constant 1 right there, right? So again, do the math, factor all the stuff out, right? You end up with 4n cubed plus n squared, and the rule above, remember, was just take the term with the highest degree, throw away all the other ones and the constants, and you end up with n cubed. So the dominating force behind the amount of time that this algorithm here takes is the number of times this for loop executes these nested loops, because that's where your n cubed comes from, right? We're not, ultimately you've thrown this away because that's this n squared over here, okay? So if you want to make this run faster, you got to focus on this code right here, okay? Here's another example. And you should be able to solve these things. What is this guy going to do? Here's a more complicated one. What do we got? We got an array of 100 items. We've got n set to 100. We're going to go through all of these elements, and we're going to fill them in with some value. It looks like j times 2, so it looks like we're filling them up with even numbers. And then we're going to set I to 0. We're going to read a number from standard in into a variable, and we're going to try and find it in there. Is the value that the person entered on the command line in this array? Okay, so what is he doing? He's got a loop in here, and he's going to execute this loop until he finds what? Until I becomes equal to n, and it stops, or the value that you're looking for is found in the array. Now, once it's found, what are we doing here? Or we run out of elements in the array. If I is greater than or equal to n, we know that we ran out of this loop and it never found it, so we print out not found. Otherwise, we know we did find it, and we say we found it, all right? So it turns out that this if then else is going to be executing one item no matter what in constant time. And we got a loop here that could go from 1 or 0 even to n times that it executes in here, plus this loop up here, which executes n times as well. So we add these all together, and what you end up with, there's like a couple of operations up here, right? You got for each one of these that are declared, we're going to call that 4 elements, right? We're going to do n here and so on. So we end up with this. The worst case is this, right? The worst case is you don't find it in this while loop. So that will execute this loop n times, right? Best case, it finds it in the first try. So that is then 1. That's down here. So let's look and see what happens. So the worst case is 4 plus 2n. The best case in this particular example is 5 plus n. Now it turns out you throw away all the constants, you still have order n time. This algorithm here, as n approaches infinity, we say runs in order n. And with that, I bid you adieu. If you want to know more, you can go to bigocheatsheet.com, and you can read about a bunch of other examples and details there. So, thanks for watching. See you next time.